Hello, my name is Sabyasachi Mishra. I am an assistant professor in the Department of Chemistry in IIT Kharagpur. In next few classes, we will discuss about the fundamental particles that constitute everything around us. Whether you see anything around you, whether living beings or non-living things, a piece of wood, a piece of metal, a stone, or the dress that you are wearing, or the food that you ate, or even our own body. Everything is made up of by same set of fundamental particles. These fundamental particles are the building blocks using which the entire universe has been created. In this lecture series, we would see the properties of these fundamental particles. We will learn about the stories behind their discoveries and their properties, their experimental validation and their significance in modern science. In last 200 years, scientists have made significant progress in obtaining a very clear understanding of the structure and property of matter. Even long ago, something about 2500 years ago, roughly around 400 BC, there were Greek philosophers who were thinking deeply about the structure and properties of the particles that make matter. These philosophers had great visions. They thought deeply about the subject. When they saw some, let us say, a stone, a metal, a piece of metal, they thought that I can break it into half, and each of that broken piece I can take and I can break it further into half, and I can continue to break them into smaller and smaller particles, until a situation would come where I cannot break this particle anymore. Then I attain a stage of uncuttability, that I cannot cut this matter any further, or I cannot divide this matter into half. This uncuttability or indivisibility of the matter is what they called as atomio. This is a Greek word which means that something which is not cuttable, you cannot cut it further. This term atomio gave rise to the term that we know today, which is atom, that is fundamental particle, and it was believed that it is something that cannot be cut further or cannot be divided into smaller pieces. These philosophers had wonderful thoughts, they were great ideas, but they were not backed up with scientific evidence. So, there were no experiments which were conducted to validate their hypothesis. It was 1808 that the first scientific theory was proposed regarding the structure of the atom or the structure of the matter. That was by Dalton in his famous Dalton's atomic theory, which was proposed in the year 1808. John Dalton was a British science teacher. He hypothesized that the matter is composed of tiny particles, tiny indivisible particles, tiny indivisible particles, and he called them atom. He imagined these atoms to be hard spheres. Now, he saw that there are different kinds of elements. There are iron, there is platinum, there is gold. So, he said, okay, I see different elements, and these elements are composed of different atoms, and these atoms that constitute an element have identical properties. Let us see. Let's imagine that we have element A, which is composed of atoms A, and we may have element B, which is composed of another set of atoms. I am showing them as spheres with dots. These are B atoms. The properties of the atoms that constitute element A are all identical. The properties of B atoms are again identical, but the properties of atoms A and atoms B are very different. So, you can imagine there are other elements. So, let us call them C. So, we have now defined 3 different elements with 3 different sets of atoms, and each atom A, atom B, atom C, they have distinct physical and chemical properties. But then John Dalton also saw that we have compounds, the chemical compounds. How do the compounds form? He suggested that the compounds are composed of several atoms with different composition or different ratio. So, different atoms of different elements combine with different ratio to form a compound. So, let us say I took one of A type atoms, I took 2 B type atom, and then I take one C type atom. So, I made a molecule or a compound which is called AB2C, because I have one A atom, 2 B type atom, and 2 B type atoms and one C type atom. This is how the compounds form. This is what John Dalton professed. Then he also saw that there are chemical reactions during which the atoms change from one compound to another. So, he described the chemical reactions. Chemical reactions is the place where the atoms are exchanged. The atoms are exchanged. Let us see, let us suppose I have a molecule which is ABC, and then I have another molecule which is BC, and they are reacting. What I get is, let us say I get AB2 plus C2. If you look carefully, you would see that the number of atoms of A or B or C type in the left hand side are exactly equivalent to the number of atoms of A, B and C type in the right hand side. During this chemical reaction, neither I created any new atom nor I destroyed any atom. What I essentially did was to exchange an atom from one molecule to another molecule. So, this is what chemical reaction was all about in Dalton's hypothesis. It was an interesting theory. It explained several experimental results, but it also had a few drawbacks. For example, it could not say why the atoms of element A and atoms of element B have different properties. So, different atoms have different properties. Dalton's atomic theory suggested that all the atoms of element A have same identical property. All the atoms of B have same properties, but atom B and atom A, they have different properties. But why should they have that? That was not explained by Dalton's atomic theory. Then here, for example, I wrote down this molecule called AB2C. Suppose this AB2C molecule exists. What Dalton's atomic theory did not explain is that why a certain composition or a certain ratio of these elements form a particular molecule, why the other compositions are not stable. Why do molecules have certain composition and why not some other ratio? These questions were not explained by John Dalton's atomic theory. Again, there were some new experiments which took place after Dalton's atomic theory was proposed, from which it was known that atoms absorb or emit electromagnetic radiations. but Dalton's atomic theory could not explain why the atoms should absorb or emit electromagnetic radiations. Dalton's atomic theory was an interesting hypothesis which described some some experimental results. However, it had many limitations. In mid 1850s, there were a series of new experiments which were carried out that showed that Dalton's atomic theory had several flaws. We will discuss about those experiments. Some of those experiments, they are called cathode ray discharge tube experiments, which were carried out during mid 1850s. Michael Faraday was one among the pioneers of this kind of experiments. This cathode ray discharge tube experiment will discuss about the experimental setup. So, it is essentially a large glass tube that you can see. It is connected to a vacuum pump using which you can evacuate the gas which is present within this discharge tube. Then it has got two metal plates. Let us draw it this way. These two metal plates were connected by a potential difference. So, a voltage was applied. So, we use this as positive terminal, this as negative terminal. So, this is negative terminal, this is positive terminal. The negative terminal is called cathode, the positive terminal is called anode. One thing that you will see is that I have kept a hole in the anode plate, the plate to which the positive terminal of voltage is connected to. There are two important things here. First, we created a vacuum. So, that means very low pressure exists, low pressure, and the second thing is that we are going to apply very high voltage. When you do that, we see in this cathode ray discharge tube experiments that several rays, they originate from this cathode terminal and they travel towards the anode. So, you would see several rays, and these rays are called cathode rays. You cannot see these cathode rays in naked eye. To be able to visualize them, what they did was create a hole in this anode plate, so that these rays can pass through this hole and come to the back side of this anode plate and will hit on this glass surface of this discharge tube. Before that, this glass tube, the side of this glass tube was coated with some phosphorescent material. Typically, one uses zinc sulphide coating to have this phosphorescent coating. The property of phosphorescent material is that when charged particle come and hit them, you would see a bright flash, a spark you would see here, a bright light you would see. That actually would be a way of visualization that these rays, which we are calling cathode rays, they have come and hit this surface, this glass surface. We will discuss some properties of this cathode rays. First it was observed that they always travel in straight line. They always travel in straight line, as it was seen. They originate from cathode and they travel towards anode. So, that is why they are called cathode rays, because they originate from the cathode terminal. And these rays also have kinetic energy. How can we know that? They have kinetic energy. How can we know that? If we can fix a propeller, a small propeller here, then you can see that these rays will hit on this propeller, and then this the fans will start rotating. So, you would actually convert the kinetic energy of these rays, which are called cathode rays, into mechanical energy. This experimental setup was taken by another scientist, J.J. Thomson, and he modified his experimental setup slightly. Instead of a cylindrical tube that you saw in the previous picture, J.J. Thomson, a British scientist, his cathode ray tube had a different shape. It looks like a bottle with an elongated neck. We will see why he has adopted this kind of shape for his experiment. Again, like a typical cathode ray discharge tube, we have one cathode terminal. So, a metal plate, cathode, we have one anode here with a hole at the center, and the two terminals are connected to very large potential difference. So, this is negative, this is positive, this is my anode terminal. First, it was this glass chamber was completely evacuated, and then a high voltage was applied across these two terminals at the cathode and anode plates. When you do that, of course, we know that rays will start from cathode and they will travel towards anodes. So, and we would see, because of the presence of this hole, the rays will come and hit this screen. This screen is again coated with phosphorescent material, so that when it hits the screen, we get a spark. Let us call this point A. All right. So, this is what we had obtained from regular cathode ray discharge tube. What J.J. Thomson did was he tried to investigate the properties of these cathode rays. So, what he did is he applied another electric field along in this manner. So, he subjected these cathode rays to another electric field. He used a particular polarity. Let us assume that we define it this one. This is the positive terminal, this is the negative terminal. When this electric field is applied, what he saw was that these cathode rays, which were going in straight line, they started getting deflected, and their deflection was in a particular direction. So, they started from here and they felt the presence of electric field, and then they started getting deflected, and by getting deflected they hit the screen at a different point B instead of point A. So, these cathode ray beams were actually bending in the presence of electric field. We know one thing is that like charges repel each other, and opposite charges attract each other. So, what we see here is that these cathode rays are getting attracted towards positive terminal, and they were getting repelled from the negative terminal. This suggested that these cathode rays are negatively charged. He then switched off this electric field, and what he did was to introduce a magnetic field. Let us assume that he used a magnet in this manner, and when he used this magnetic field, he saw that these cathode rays, so before he introduced the magnetic field, he switched off the electric field. So, that means the cathode rays, instead of hitting the screen at point B, they came and hit the screen at point A. Now, again by introduction of a different field, this time it is magnetic field, the cathode rays again get deflected, but this time they are getting deflected to another opposite direction. Let us call that where the point where the cathode rays hit the screen, let us call that point C. So, now using these two setup, one was electric field, another was magnetic field. One was electric field, second was magnetic field. By using these two different fields, J.J. Thomson showed that these cathode rays are getting deflected in opposite direction. Now, we have got two different fields whose strength we know because we are doing the experiment on that. Now, if we think why these cathode ray beams are getting deflected, we think that okay, of course, they are charged particles. In addition to their charge, they also will have some mass, because if a particle has different mass, you would require a different amount of field to deflect it by a certain magnitude. So, the deflection, the degree of deflection depends on two properties of the particle. One is charge and the other one is mass. What J.J. Thomson did is that he adjusted the electric field and magnetic field. Now, he switched on both electric field and magnetic field simultaneously, and he adjusted the strength of the electric field and the magnetic field in such a way that the cathode ray beam, instead of getting deflected towards point B or getting deflected towards point C, was brought again back to the straight line, and it can be achieved by carefully tuning the strength of the electric field and the magnetic field. So, we have two field strengths that we can tune, and we have two different properties on which this deflection depend. On the basis of several careful experiments, it was obtained that these particles, the cathode rays, they have a fixed value of E by m, which was determined to be 1.758 into 10 to the power 11 Coulomb per kilogram. Right. This is very interesting. So, he saw he could get an estimation about the charge per mass ratio. He repeated this experiment by changing this metal from one metal to another metal by using different metals for cathode and anode, and he saw that no matter which metal he is using as cathode and anode, the E by m ratio remains the same for all metals. This is very interesting, because to begin with, this cathode ray discharge tube was completely vacuum. There was nothing inside this tube except for the cathode and anode terminal. Now, by passing high voltage, some particles which have certain mass, certain charge, certain value of charge per mass ratio, these particles they are created, and these particles have same E by m value irrespective of the nature of the material. So, that means there are two things. One is that now John Dalton's hypothesis said that atom was the smallest building block, the tiniest particle that you can see. But here J.J. Thomson said that no, there is another particle which is negatively charged, and this negatively charged particle is present in all metals, different elements. So, there exists another particle which is fundamental in nature and is present in all the metals that he tried out. So, he suggested, so there is something other than atom which is a fundamental particle. Now, what he obtained from this experiment was the charge to mass ratio, but he neither had an estimation about the charge of this particle, nor did he have an estimation about the mass of this particle. And this was resolved by another set of experiment, which this time it was carried by Robert Millikan, This experiment is very interesting. It is called Millikan's oil drop experiment. The experimental setup looks something like this. You have a large chamber which is fitted with two metal surfaces. You have one metal surface at the bottom, one towards the top, and the top metal plate has a hole, it's a tiny hole at the center of this plate. To this chamber, Millikan connected a thing that is called an atomizer. This is an atomizer. Atomizer is nothing but a mechanism with which you can create small particles. It is also used, for example, in the perfume that you use. You press the perfume and then you see small particles coming out of the perfume, and they are very tiny particles. So, this is this has similar mechanism, and this atomizer was connected to some oil. So, when you press this atomizer, you actually create lot of oil drops here in this part of the chamber, and these oil drops, because of gravity, they will come down, and since there is only one small hole, these oil drops will come out of this region of the chamber only through this hole, and they will travel downwards because of gravity. Because of gravity, which is pulling the oil drops down, they will come down. What he did was to introduce a small telescope here. What would he do with this telescope? He can look at the motion of these oil droplets when they travel along this direction through this telescope. By doing this, he can monitor how long these oil drops are taking to travel in a distance. From there, he can have an estimation of the mass of these oil droplets that his atomizer is creating. So, we have an initial estimation about the mass of these oil droplets. All right. This was not the end of this arrangement. He connected these two metal plates to a potential difference. Let us say that we have there is a battery here. So, we have the positive terminal this side, negative terminal this side. Of course, when I apply a potential difference, if these oil droplets are chargeless, this is not going to affect them. They will simply go by gravity. It is not only gravity which is actually playing a role, there is also a role of viscosity, because we are creating these small droplets, and when they go down in the air, there is a viscous force, but for our discussion we will ignore that. We will consider that only because of gravity these oil droplets are coming down. Now, what he additionally did is that he introduced X-ray in this manner. When he introduced X-ray, X-rays are radiations with extremely high energy. They have so much of energy that they can ionize the gas present within this chamber. So, when you apply the X-rays hit the gas molecules and they ionize them, and when they ionize them, these gas molecules release negatively charged particles, and these negatively charged particles stick to our oil droplet. So, now I had this oil droplet, but this is now sticking with some negatively charged particles, right. Now, after introduction of this X-ray, these oil droplets are no longer chargeless. Now, they have a certain charge, and I am applying an electric field depending on the polarity of the electric field that I have chosen. Now, you can see, because these are negatively charged oil droplets, they would be attracted towards the positive plate. So, they will go upward. So, now there is another field, that another force because of electric field, which will pull this charged droplet upwards, and gravity is anyway pulling it downwards. Now, we have two different forces. The gravitational forces can be written down as mg, and the electric forces due to electric field can be given as QE. E is the strength of the electric field that I am applying, and Q is the charge of this oil droplet. Now, if I use a very strong electric field, which is much stronger than gravitational pull, then of course you would imagine that these oil droplets will suddenly go up and will stick to the upper plate. If I use a very weak electric field, the gravitational pull will win and this oil droplet will come downwards instead of going upwards. But if I can carefully manage or carefully tune the strength of the electric field, I can attain an equality where QE, the upward pulling force because of electric field, will be now equal to the gravitational pull, which is mg. G is a universal constant, I know that. Mass of the oil droplet, I have an estimation already. E, the strength of the electric field, that I know because I am doing the experiment. The only unknown that I am left with is the charge on these oil droplets, which are called Q. So he tried out different values of electric field and he saw that he was getting some interesting values for the charge. So he was getting sometimes he was getting 1.6 into 10 to the power minus 19 coulomb, sometimes he was getting 3.2 into 10 to the power minus 19 coulomb, sometimes he was getting 4.8 into 10 to the power minus 19 coulomb, and so on and so forth. If you look carefully at these numbers, you see that all these numbers are integer multiple of this value. So what he was getting was as charge as the integer multiple of 1.6 into 10 to the power minus 19 coulomb. From his experiments, he concluded that the base elementary value of this charged particle is 1.6 into 10 to the power minus 19, and if two of these particles are sticking to the oil droplet, he is getting 3.2, and if he is three of these particles are sticking to this oil droplet, he is getting 4.8 into 10 to the power minus 19 coulomb, and so on and so forth. But the basic value, the fundamental value, comes out to be 1.6 into 10 to the power minus 19 coulomb. So he suggested, so this must be the charge which we call it Q, and we call that the charge of the electron must be 1.6 into 10 to the power minus 19 coulomb. Since already we know that these are negatively charged, we can use a negative sign here. From previous experiment, that is the experiment of J.J. Thomson, we had an estimation of E by m as 1.758 into 10 to the power 11 coulomb for kilogram. Now we have an estimation of E, we have an estimation of E by m. From these two equations, I can get this the value of n, which is 9.01 into 10 to the power minus 31 kilogram, which is now the mass of this fundamental particle, which has a negative charge of this value 1.6 into 10 to the power minus 19, and this particle we called electron. If you look at this, the mass of this electron, it turned out that it is several thousand times smaller than the smallest atom that was known, that is the hydrogen atom. So Dalton's hypothesis was that the atom is the smallest indivisible particle. There is nothing inside the atom. Atom is the basic building block, but because of the experiment of J.J. Thomson and Robert Millikan, it turns out that all elements have these electrons which have a particular value of mass which is much smaller than the mass of an atom. So therefore there exists a particle which is smaller than an atom, and these particles have negative charges. Now this was wonderful. However, there is one problem. The problem is that these fundamental particles, which we call them electron, are negatively charged, but atom as a whole is charge neutral. So there was a need to propose a new model for atom, and this is what was done by J.J. Thomson in his famous Plum-Pudding model of atom. He said that the atoms undoubtedly have electrons which are negatively charged particles. So to counter these negatively charged particles, there must be a positive charge in the atom. So he imagined that atom is a atom is spherical. He said that okay, the positive charge must be distributed uniformly over the atom. So, the positive charge is uniformly distributed. So, there is a positive charge density over the atom, this is what he believed, and then electrons, which are the negatively charged particles, electrons are embedded into the atom or the positive charge, to the positive charge density. He imagined the atom to be something like this, as is shown here. The atom is spherical in shape, the green color shows the positive charge distribution, and the blue colored dots that you see, they are electrons which are embedded randomly in this positive charge distribution of the atom. He likened it to the famous British dessert Plum-Pudding model. This is what is called Plum-Pudding model, which can also be imagined in terms of watermelon. You see the watermelon, the flesh, the red flesh of the fruit part of the watermelon can be imagined to be the positive charge distribution, and the seeds, the black seeds that you see are essentially the electrons which are embedded into this fruity part of watermelon. You can call it Plum-Pudding model or watermelon model. This was a revised version of the model of atom, which was proposed by J.J. Thomson, which is a one step advancement of Dalton's atomic model, because Dalton did not imagine the presence of electrons. He just said that atoms are hard spheres. But then there were a series of experiments which were carried out that suggested that J.J. Thomson's Plum-Pudding model is not that accurate. It has got its flaws. We will look at those experiments now. One such experiment was carried out by Ernst Rutherford, which is famously known as Rutherford's gold foil experiment, that was carried out in the year 1911. The experimental setup is shown something like this, where you have a large circular screen. You have a large circular screen which is coated with phosphorescent material. Again, you can use zinc sulphide. So, the inside is coated with phosphorescent material. He has used a gold foil here. Gold foil is a very thin foil that is kept in this way. It's just like a piece of paper. He has a source of alpha particles. You can imagine it like a gun which emits alpha particles. Alpha particle is simply doubly charged helium. So, these are positively charged particles with known masses. So, what he does is that there is a gun in this source that shoots alpha particles, and these alpha particles they are passed through a lead plate, and then these alpha particles they hit the gold foil like this, and if they pass through the gold foil, they will come and hit the screen at this point. These, as I said, these alpha particles are positively charged particles, and this is coated with a phosphorescent material. The characteristic of this material is that when it is hit with a charged particle, you see a spark, you see a bright light here. So, this experiment was carried out in dark rooms. All right. So, what he did is that he started shooting alpha particles after alpha particles, thousands and thousands of alpha particles, and he tried to see where these alpha particles are hitting in this screen. What did he observe? He observed first the most of these alpha particles, they go undeflected. Undeflected means these rays simply travel in straight line as if there was no barrier. That was one primary observation, that most of these alpha particles are just going through the gold foil as if nothing is there on their way. But he also saw a small number of alpha particles, they undergo small angle deflection. What is that? When these alpha particles come, they hit here this on the gold foil, and instead of going straight, they go like this, and they hit the screen at different point, or it can also go and hit somewhere. But this happens only in some small number of cases. Very rarely, but it is a significant observation, rarely there is a phenomenon of bouncing back. The ray, the alpha particles simply bounces back. So, that means it goes and hits this gold foil and it comes back, or it undergoes a large angle deflection, and it hits the screen somewhere in this region. It either bounces back or very large angle. These are the three primary observations that he made. First, most alpha particles go through this gold foil undeflected as if this foil does not exist, as if there is no barrier on their path. A small number of alpha particles, they undergo small angle deflection, that means something is obstructing their path, and only rarely, they calculated about 1 in 20,000, 1 in roughly 20,000 alpha particles, they actually either bounce back or undergo very large angle deflection. Now, this was an interesting observation, but it required some amount of thinking as to what might be happening. Now, you imagine that this is your gold foil, which is very thin foil. So, there is only the thickness is extremely small, in the order of a few nanometers. You can imagine in the following way. Imagine that this is your gold foil that you saw that was standing within the circular loop, and I am showing you the cross section from this direction. You see that, well, the gold atoms, since the foil is very thin, I imagine only a few layers of atoms are present. I do not know the structure of the atoms, but I know that this gold foil is composed of some atoms. Let us first imagine if Dalton's atomic theory were true, what would have happened? So, I am shooting these alpha particles. I am shooting these alpha particles. If Dalton's atomic theory were correct, we would have seen that these hard spheres would have deflected these particles. So, most of the times the alpha particles would have come back, but that was not the case. What was observed is that most of the times these alpha particles, they pass through that. So, they were going through like this. Since most of the times they were going through, his first conclusion was that atom has a lot of empty space. That was the first conclusion, because these alpha particles felt nothing, they just simply passed across the gold foils as if nothing was there. So, the atoms must have lot of empty space. This is what he concluded. Fair conclusion. The second thing is that what he saw is that when some cases, when the alpha particle was coming, it saw something, we do not know what, but it saw something because of which it got deflected. Instead of going straight, it
went this way, it underwent some deflection. Why would that happen? That could happen if we remember these are positively charged particles, they have certain mass, these alpha particles. These positively charged with certain mass particles, they are going and they are getting deflected. It might have happened that there are some positive charges in this atom, which is actually repelling the alpha particles that are coming, and these positively charged particles have certain mass, because of which there is a collision and then there is a deflection. So, from this it turned out that, well, the atoms have some positively charged particle with some mass, right. That is why you see some deflection. But what was the third observation? That was only rarely 1 in 20,000 times that you saw that this was the ray that was coming was getting completely was bouncing back. When would that happen? The complete bounce back will happen only when if the ray, the alpha particles that were traveling hits a massive charged particle, positively charged particle. If it hits directly, then the complete retracing of the alpha particle pathway can be observed. So, from the second observation, it can be concluded that atoms have positively charged particle with mass, and these positively charged particles with mass, they are concentrated at one place. Only when the alpha particles hit this particular place where the charge and mass are concentrated, you see this bouncing back. By carrying out this experiment several times, he concluded that by then it was known that a typical atom had the size of 10 to the power minus 10 meter. So, this positively charged core with mass must have the size of 10 to the power minus 15 meter, and this core that we call, which is where all the masses are concentrated and the charges are concentrated, it was called as nucleus. So, from Rutherford's gold foil experiment, it was learnt that the atoms have a core which is known as nucleus, that where the charge and the mass are concentrated. So, now we can propose Rutherford's atomic model. So, he imagined that atom has a central place, the nucleus, which contains the mass and the charge, positively charged, and the electrons, they go around the nucleus in fixed orbits. We can imagine, we can reimagine this experiment by considering that what would be the outcome, what would be the observation if J.J. Thomson's Plum-Pudding model were true. Plum-Pudding model would have said that the positive charge is uniformly distributed. If the positive charge were uniformly distributed, you would have seen that the most of these alpha particles would have got deflected. But that was not the case. Since only a few particles got deflected and very rarely you saw a complete deflection, it was said that the Plum-Pudding model was wrong, and here comes a new model for atom which says positive charge of the atom is centered at a core place, that is called nucleus, and the electron, which carries the negative charge, they go around the nucleus. This is the story of the discovery of nucleus.
In the next class, we will discuss about the internal structure of the nucleus. We will see that the nucleus is composed of neutrons and protons, and we will also learn about the stories behind their discoveries. Thank you.